Suppose I have a box and I shove it across the floor, giving it a speed v, and then let go, and it slows down and stops. So it's v equals 0 at the end. That means its acceleration is opposite the velocity during that time. Okay. Now, why does it slow down? Well, it's because there's a frictional force acting in the opposite direction of the displacement. The displacement is this way. Okay. So we could try and use energy to try and analyze this and think, okay, if my system is a box, then I can do the work kinetic energy theorem. Okay, this is true for point particles. Okay, and then I could treat my box as a point particle and say, okay, I could find the change in kinetic energy based on the work done, or vice versa. Okay? And so our question is, well, what's the work done? It's a force times the displacement. More particularly, the force in the direction of the motion. So our displacement we'll call delta S. We would get, in this case, our force is a friction force and its opposite. So we'd get a negative Fk delta S. All right, and that's going to equal K final minus K initial. All right, which is good because I should lose kinetic energy. It's slowing down in this case. K final is 0, so I have an overall minus on this side, which matches the overall minus on this side. Okay, so that seems to work out just fine. It seems consistent. It makes sense. But there's a problem with this one. Okay, and I'm going to illustrate that problem by talking about warming up your hands. So instead of trying to draw it, here's my hands. And in the wintertime when it's cold, you go like this. You rub your hands together to warm them up. Okay, now each hand is applying a frictional force, a kinetic frictional force on the other one. And it's not gaining any kinetic energy or losing any kinetic energy, but they are warming up. Okay, so this rubbing motion is creating heat in the palms of my hand. Okay, so if I think about one hand, and forgive me, these are horrible drawings. Okay, which one is my system? All right, now when I decide maybe this one's my system and this one's external, and the frictional force is between this, but this one warms up too. They both warm up. And because that frictional force puts energy, thermal energy, into both things that are experiencing that frictional force, I can't exclude one. The system is both hands. So the same thing would happen with this box. As this box flies forward, the frictional force would actually warm up the bottom of the box. The molecules in the bottom of the box would heat up, but so would the floor, just like the two hands would. So even though this works out mathematically, conceptually it's got that huge flaw. So to take care of it, what we can do is expand our work kinetic energy theorem and say for systems that can have thermal energy, even if we can model it as a point object in terms of its position and such, if we can say, oh, it can take thermal energy, it can heat up, well, then we have to include our system to include all things interacting via friction. And so external to the system are only those things that are applying forces not like friction. Okay, we can say that's non-dissipative forces. So friction is a dissipative force, which causes an increase in thermal energy. So now we can have delta K of our system plus delta E thermal. And I could technically put of our system here, but we'll specify systems generally. And so this thermal energy will grow in my system if there's any friction. So friction's not over here anymore. It's on this side. So in this case, we'd have 0 equals a delta K of my system, okay, plus a delta E thermal of my system. All right. And the thermal energy grows because the kinetic energy decreases. So I'd get the same negative, this would be negative here. I get the same negative here, and this one grew. And so we define thermal energy to be equal to the frictional force times the displacement. No minus sign, because this always grows. Thermal energy can never get smaller from friction. It always gets bigger. Okay, so this is our new definition of thermal energy, but what's really important is it is always inside the system. Okay, and so any two objects interacting via friction are in the system.